Thank you very much for this opportunity to give this short presentation today. My name is Pascal and I'm a second year PhD student at the Cavendish Astrophysics Group in Cambridge. So far I've been analysing closure phases from HERA, and in this presentation I'll give some upper limits on the epoch of reionisation that I obtained doing this analysis. Before I start, I'd like to acknowledge that this work was done in collaboration with other people from HERA, and in particular Bojan Nikolic, Chris Carilli and Nityanandan Tyagarajan. I'll just give a quick review of the epoch of reionisation and HERA. So the epoch of reionisation marks the time in cosmic history where the first luminous sources started to ionize the neutral intergalactic medium. And the aim of HERA is to measure the 21 centimeter emissions of neutral hydrogen during that epoch. More precisely, it aims to do that in a statistical manner by measuring the power spectrum. The most intuitive way of doing that is using visibilities. These are the most fundamental quantities of radio interferometry, and the reason is that visibilities are essentially Fourier modes of the sky, and therefore they map nicely to the power spectrum. However, this process is complicated by the fact that the cosmological signal is extremely weak in contrast to the very bright foregrounds. That means that any data processing and the calibration need to achieve a fractional accuracy that is greater than the dynamic range required to measure the weak signal. And the question is, are there other interferometric quantities that we can use to bypass some of these processing steps, and in particular the calibration? The answer is yes. Such quantities are called closure quantities, and here I'm going to focus on the closure phase. In an antenna triangle there are three visibilities. And visibilities are complex numbers, so they can be written as an amplitude times a complex phase. And the complex phase can be further decomposed into a term that is purely due to the sky and another one that is due to the instrument. And here we make the assumption that the instrumental gain phases are antenna-based and direction independent. So the instrumental phase here consists of two parts, one gain phase for each antenna that is involved in forming the visibility. The important thing to note here is that among these three visibilities, each gain phase appears twice, once with a plus sign and once with a minus sign. The minus sign is due to the complex conjugation in the correlation process. So we can add these phases accordingly in order to eliminate all of the instrumental phases, and what we are left over with is the closure phase. And in a way, the closure phase is a true representation of the sky. Closure phases have some very interesting properties. Firstly, closure phases are independent of antenna-based direction-independent gains. That is what we showed on the previous slide. Secondly, closure phases are invariant on the translation of the apparent sky. That can be shown using property 1. So adding a gain phase to one of the antennas doesn't change the closure phase, but it is equivalent to tilting the aperture plane or shifting the sky. So the closure phase does not depend on that. Thirdly and lastly, the closure phase has values of 0 or pi for point symmetric brightness distributions. Again, we can use property 2 to shift the center of symmetry onto the origin of the image plane, where the visibilities have values of 0 or pi, and so the closure phase also has a value of 0 or pi. This is important to understand how the closure phase responds to strong point sources, and where the closure phase will have values of 0, and also RFI, which will try to force the closure phase to 0. There are more interesting geometric insights which can be found in this paper published earlier this year. And one more time to highlight that these properties only hold in the absence of baseline and direction dependent effects, one of these effects being different antenna beams, for example. So now back to 21 centimeter science and how we can use the closure phase to detect the EOR. So the idea here is that the 21 centimeter fluctuations will also be partly recovered in the visibility phases and should therefore also show up in the closure phase. So in analogy to the visibility approach, we can perform a delay transform of the closure phase, which is essentially a Fourier transform along the frequency axis. Now actually we use the complex exponential of the closure phase to avoid the discontinuities that arise due to the circularity of a phase. We also have a scaling constant, which is our effective visibility here. This makes our closure phase delay spectrum have the same units as a visibility delay spectrum. Now this plot here I've taken from the paper here, and it shows simulated delay spectra for visibilities and for the closure phase side by side. I'll start by focusing on the visibility delay spectrum. The solid lines show the delay spectrum for a sky that contains foregrounds only, while the scatter points also include the EOR. So as we expect, the spectrally smooth foregrounds are confined to low delay modes, while the rapidly fluctuating EOR also occupies higher delay modes at which we can separate the signal out. Remarkably, the closure phase delay spectrum looks very similar to the visibility delay spectrum. The EOR also separates out at high delay modes, and the dynamic range is very similar. The main difference is that the foreground region is a lot broader. And the reason for that is that the complex exponential of the closure phase translates to a triple convolution in delay space, which effectively broadens our foreground region and mixes K modes. So we see there is here a disadvantage of this approach. Nevertheless, there is a wide delay region in which we can separate the EOR signal from the foregrounds. Lastly, our y-axis is in pseudo units. This is to highlight that our scaling is dependent on our choice of effective visibility, and also to avoid any confusion with the physically more intuitive visibility delay spectrum. So now that I've hopefully motivated the use of closure phases, I'll quickly outline the development of this method so far. So in 2018, first simulations were published that showed that it is in principle possible to detect the EOR using closure phases only. Then in 2020, a more rigorous mathematical development was published, which treated the 21 centimeter fluctuations as a perturbation to the foreground closure phase. It was therefore able to make a direct link between the visibility delay spectrum and the closure phase delay spectrum. In the same year, the first results were published for phase 1 HERA data, comprising 18 nights and 2 fields, each 22 minutes in duration, and 31 equilateral 29-meter triads. The results I'm showing you in this presentation are also derived from the same data, phase 1, 18 nights, but 3 different fields and 2 bands, and 2 different triad classes, equilateral 14-meter and equilateral 29-meter triads. Now the 3 fields and 2 bands that I analyzed correspond to the same fields and bands that were used to publish the first visibility upper limits. And so it allows for a nice side-by-side comparison. I'll quickly walk you through my analysis pipeline. I start off with raw visibilities from HERA, but also with simulated visibilities, which allow to compute a scaling coefficient and also to compare cross-power spectra in the end to see whether we are limited by noise or systematics. So we form closure phases and we align them on an evenly spaced LST grid. This allows us then to average different observing nights. We do this using a median, which effectively filters out any time-dependent RFI. And we do the averaging within 2 different observing night bins. We then form the delay spectra and form cross-power between different delay spectra in the 2 observing night bins. This again minimizes the risk of any time-dependent effects leaking into our cross-power. Then lastly, we do some incoherent averaging, over different polarizations, times, triads, and absolute delay bins. This is of course assuming that the signal is unpolarized and isotropic. So here's an example of one of my results. Here I have only averaged cross-power spectra between different triads of the same triad class. This is to ensure that systematic effects which are triad-based and coherent among different observing nights still average down. So here on the right is an example for field 1 band 2 and equilateral 28 meter triads. The top plot is the data cross-power spectrum and the bottom plot the model. And as we see, the noise-dominated regions are very similar. This is also backed up by the Kolmogorov-Smirnov test here, which rejects the null hypothesis that the data and model follow different distributions. So one difference is this bump here at 1 microsecond. This is a spectral ripple, which is well known and probably due to some combination between cable reflections and cross-coupling effects. But still, we have data points here above 1.5 microseconds and here between the foreground region and the systematic region that we can use to set upper limits on the epoch of reionization. So unfortunately, not all results look as good as the ones I just showed. So this is an example of band 1 data, which is affected by a narrowband RF5 feature here at 125 megahertz. This feature is very persistent and therefore is not filtered out by our median averaging, and as a consequence the data cross-power spectra has a plateau at high delay modes, which doesn't average down as we add more data. So for future analysis we'll have to flag RF5 features like this and in-paint them using a deconvolution algorithm, and this will hopefully allow us to also set upper limits on data that is affected by RFI. This slide summarizes some of the best results obtained in this analysis. The cross-power spectra here are now in cosmological units. So the top two plots are equilateral 14 meter triads, and for the bottom two are for equilateral 28 meter triads. On the left we have field 2, on the right field 3, and this is all band 2 data because band 1 is affected by RFI. As we'd expect, the limits for equilateral 14 meter triads are slightly lower than for equilateral 28 meter triads. This is simply because there are more equilateral 14 meter triads in the array, so we have slightly more data that can be averaged. Now the best upper limit we get from this point here. This is between the foreground and the systematics region, and our condition for including points like this was that the error bar should cross 0. On this slide I'll compare our upper limits to the upper limits of other experiments. So on the y-axis we have here the upper limit in millikelvin squared, the x-axis are the k-modes, and the color is an indicator of redshift. Now the right pointing triangles are the upper limits obtained in this analysis. Below we have the diamonds, which are the visibility upper limits from the HERA collaboration. And there's one caveat about this, namely that our upper limits are in pseudo units, meaning that this comparison is only approximate. So we see that we are a bit more than one order of magnitude above the best upper limit obtained with visibilities, and the reason for that is that we don't have access to such low K modes. If we make the comparison at similar K modes, then we're only about a factor of 2 less sensitive. And the reason for that is that we don't really combine different triad classes. That is because there's no really obvious way of doing that. Whereas with visibilities, it's a lot easier to combine different baselines doing spherical averaging. So for future analysis, we'll try to combine different triad classes. We still have to figure out what the optimal way is to do that, but that will probably increase our sensitivity by a bit. So to wrap up, we have performed the analysis on 2 bands and 2 fields with closure phase only. and there are still about 3 orders of magnitude to go in a millikelvin squared until we reach the level of fiducial EOR models. At the moment, we are analyzing an extended data set, the internal data release 3, which contains more than 100 nights worth of data. So we expect a significant improvement in sensitivity there. So our main message is we have an approach here which is very straightforward to perform. It only requires few processing steps and there is no calibration needed. And so we expect fewer errors and systematics. Thank you very much for your attention.